Good morning, second grade. Well, as I promised yesterday, today we're going to look at Seymour Simon's Lightning. It's going to have a little science today. I know I've sent some science home in your packets, but we can have fun with the science book today too. So, Lightning by Seymour Simon. Every second of every day, more than 100 lightning bolts strike the earth. That's about 10 million lightning bolts in a single day. The early Greeks thought that the king of the gods, Zeus, hurled thunderbolts from stormy skies. The Vikings imagined their god of weather, Thor, striking a powerful hammer against an anvil to produce thunder and lightning. Native American tribes believed that lightning was caused by the flashing feathers and flapping wings of the mighty thunderbird. Today, we know that lightning is a river of electricity rushing through an ocean of air, yet scientists are still not sure of exactly what causes these awesome strokes of power. Lightning bolts travel at lightning speeds of up to 60,000 miles per second. That's 6,000 times faster than our fastest spaceships. A single lightning bolt travels through the twisted paths in the air about as wide as one of your fingers and from 6 to 10 miles long. A flash of lightning is brighter than 10 million 100-watt light bulbs, and it pulses with hundreds of millions of volts and billions of watts, as much power as there is in all the electrical generating plants in the United States that in that split second. But because the flash only takes a millionth of a second, the electricity in a bolt would power one light bulb for only 1 month. Lightning begins with violently moving ice crystals and raindrops in storm clouds. As a result of the motion, electric charges build up at the bottom of the cloud. An opposite electric charge builds up in the ground just below the cloud. The charges in the ground can make can make your hair stand on end right before a lightning storm. Starting in the cloud, small streamers of sparks called stepped leaders begin to shoot downward at 50-yard leaps. As the leaders approach the ground, they meet upward streamers from the ground, most likely from high places such as treetops and tall buildings. When the two streamers meet, their paths form a channel, and a lightning bolt is born. Though this kind of lightning seems to shoot down from the clouds, what we actually see is the return stroke of the electricity flashing upward from the ground. This is a photo of a lightning bolt striking a 65-foot tree. Besides the main bolt, you can see two smaller upward discharges, one to the left of the main bolt, reaching up from the branches, and another reaching up from the antenna on the farmhouse at the left. Trees sometimes survive direct hits because the electricity passes over their wet surface and into the ground. 10 years after this tree was hit, it was still standing. Lightning sometimes strikes the ground and tunnels downward into the soil. The intense heat of the electricity fuses the sand particles together in the shape of the bolt's path. The resulting tubular crust is called a fulgurite, after the Latin word for lightning. Some fulgurites are longer than 10 feet. Okay. Here you can see the lightning hitting the tree. And there's that little upward strike. And as he said, if we get over here, it's really, hang on, it's really dark. You can also kind of see this little lightning coming up off the house. And then, try to get this so you can see it. That's a fulgurite. As you can see, it looks kind of like a tree root, but it's actually soil fused by lightning. Perhaps the most famous experiment to show that lightning is electrical took place in 1752 when Benjamin Franklin flew a kite during a Pennsylvania thunderstorm. As lightning flashed, sparks jumped from a key fastened to the bottom of the damp kite string. A silk ribbon attached to the string insulated Franklin's hand. The museum model seen in the photo demonstrates lightning striking a kite, which conducts electricity to a light bulb. This highly dangerous experiment can be shown in a much safer way at home. On a dry day, drag your shoes along the carpet, and then touch a metal doorknob and watch the spark jump. For an instant, you become a thundercloud by gathering charged particles, called electrons, from the carpet. When you reach for the doorknob, electrons stream from your hand in a tiny lightning bolt. And this is the simulation of the key. Scientists have replaced Franklin's kite and key with small rockets trailing long copper wires connected to electronic instruments. The rockets are launched from the ground into a passing storm cloud. The wire creates a path for the lightning bolt, and in an instant, the wire is vaporized. The strike is measured and recorded by the instruments and safely studied by the scientists. Photography is another useful tool scientists use to study lightning. A single lightning discharge is made up of 20 or more strokes, one after another, in a fraction of a second. Swinging a camera with its shutter open during a lightning flash shows the many repeat strokes during the single flash. Each stroke takes place too fast for the eye to see, yet slow enough to make lightning seem to flicker. And you can see where the when a lightning bolt strikes, the electrical energy quickly changes into heat. Temperatures in the path of a lightning bolt can reach as high as 50,000 degrees. That's 50,000 degrees Fahrenheit. 5 times hotter than the surface of the sun. The intense heat alongside the lightning channel makes the air expand explosively and then contract as it cools. This quick back and forth movement of air particles produces the sound waves we call thunder. From close up, we hear thunder as a single sharp crack. From farther away, thunder seems to roll or rumble in the distance. When a lightning bolt flashes, we see it immediately, but thunder takes about 5 seconds to travel a mile. That's because light is about 1,000,000 times faster than sound. There's a way to measure how many miles lightning is from you. Start counting the seconds when you see a lightning flash, and stop when you hear the thunder. Just divide the number of seconds by 5. So if you hear thunder 5 seconds after the flash, the lightning was 1 mile away. 15 seconds means that it was 3 miles away. There are 3 main kinds of lightning. Intercloud lightning is the most common. It occurs when lightning arcs between oppositely charged centers within the same cloud. From the outside, it looks like the cloud just suddenly flickers and brightens, then produces rumbling thunder. Cloud to ground lightning is the most dangerous form. It is the kind that we know most about. The third kind, intercloud lightning, occurs when lightning leaps across a gap of clear air between two different clouds. As you can see, we have this big cloud here, and then we got this other cloud here, and the lightning is shooting the gap. You may have heard of other types of lightning. Usually, these are just different names that describe the lightning to describe when lightning comes or how it looks. For example, heat lightning occurs when it's hot. Summer lightning happens in the summer. Sheet lightning seems to come in flat waves, and ribbon lightning looks like streamers flashing through the sky. Silent lightning appears without sound because it is so far away, and colored lightning seems to flash red or blue. Ball lightning is a bright round spark that seems to float in the air. Okay. So, there's ribbon lightning. This is sheet lightning. It's kind of when it looks like a flash bulb goes off. And if you look really carefully, this is ball lightning. It's in the summer of 1995, scientists discovered a new kind of lightning, which they named elves. Elves are very bright, short flashes of lightning that blaze forth high above the clouds at the very edge of space. They can last for less than 1,000th of a second, quicker than you can blink. The color of elves is not yet known, but it is thought to be green. Two other recently discovered high-altitude kinds of lightning are called jets and sprites. Jets are fast-moving fountains or sprays of blue light that burst upward from the tops of storm clouds to an altitude of about 20 miles above the clouds. Pilots have reported seeing columns of blue or green light above thunderheads for years, but they have only recently been videotaped. This is one of the first true color images of a red sprite, photographed from an altitude 60 miles over a thunderstorm in the Midwest in July 1994. The white-blue flash below the sprite is normal lightning at the tops of the clouds. Okay, so this is the normal lightning. And then this is the sprite. The National Lightning Detection Network is a web of at least 130 magnetic detection finders that cover the entire United States. The detectors are used to locate cloud-to-ground lightning flashes. Information in the form of a grid map shows lightning across the country. Spectacular lightning is common in Tucson, Arizona. During the summer's rainy season, thunderstorms can generate more than 10,000 strokes per night. These summer thunderstorms erupt when the moist air flows from the Gulf of California and is forced upward by the nearby mountains. The rising moisture condenses into thunderhead clouds that tower into a mushroom shape, reaching 60,000 feet above the ground. Because of Tucson's high clouds, the lightning here is the most dramatic to be found in North America. This is a 5-minute exposure photograph of such a storm. The view from a hill overlooking Tucson. This photo of a storm over Florida's Lake Okeechobee spells double trouble. lightning, and a twisting tornado called a waterspout. Florida is the lightning capital of the United States. The high humidity and heat produce almost daily summer thunderstorms, and 3 times the number of lightning strokes of any other place in the country. In fact, 10% of the people struck by lightning in the United States live in Florida. But lightning strikes every state, sometimes very frequently. In March 1991, more than 15,000 lightning strikes resulted from a single 6-hour storm stretching over Iowa, Illinois, Wisconsin, and Missouri. During that storm, the skies blazed with almost constant lightning. Okay, now this is the Florida photo. Here's the waterspout. And here is the heavy lightning strike. I've been to Florida and on vacation with a friend, and yes, we could almost set our watches by the daily summer thunderstorms. We usually roll in about 3:30 or 4 in the afternoon. But lightning can be made in a laboratory by an instrument called a Van de Graaff static electricity generator. It can generate millions of volts of artificial lightning from a metal sphere mounted on top of an insulating column. In this demonstration at the Boston Museum of Science, the man in the metal birdcage is protected from the flashes of lightning made by the generator. The electricity passes through the metal frame and goes into the ground without harming the person inside. Grounded metal wires surrounding the exhibit protect the visitors in the same way. Hardtop cars can shield motorists during a thunderstorm for the same reason, and grounded lightning rods can protect buildings. Okay, here's the Van de Graaff generator. It's a very big one. And we can see right here, this guy in the cage. The lightning goes around through the metal of the cage and doesn't harm the human inside. Don't try this at home. Lightning kills about 100 people per year in the United States. Yet 250 more are hit by lightning each year and still survive. If you are caught out in the wide open in a lightning storm, stay away from places that are most likely to be hit. High ridges, open meadows, telephone poles, wire fences, rails, wet beaches, and single tall trees. A hard-top car is safe. Bikes and open vehicles are not. The best thing to do if you feel tingly or your hair begins to stand on end is to crouch down with your hands off the ground and become a basketball with legs. Don't lie down because the ground can carry a charge. If you are in water, get out as soon as possible. That's why workers at a water park near Tucson have to keep watching the approach of distant storms. They also use lightning detectors that can register unseen flashes in the clouds above. And again, you'll probably want to get out of the pool if you see this. Scientists say that the recent discoveries of elves, sprites, and jets make it likely that there are more forms of lightning that we don't know anything about yet. Lightning flashes may even have been detected on other planets, such as Jupiter and Venus. Despite all we have learned since Ben Franklin's experiment over 200 years ago, lightning remains a mystery that we are only slowly beginning to understand. Okay, second grade. This is what you're going to do for today's book, because I want to see what you remember. This is a glossary. I want you to write in your notebook what a glossary does, what you use it for. This is the index. I want you to write in your notebook what the index is for. Okay? See if you remember what those are for. So that would be super easy. A couple sentences. Remember to stay safe in lightning. Right now, we haven't had too many storms yet. But as the summer comes in, if you're just aware of it, you pay attention, and you're really careful, well then you don't really have to be scared of the lightning. Even though storms can still be a little scary, and it's okay if you're a little bit, but don't worry about it. Okay, so there's science. There's your science lesson for today. Tomorrow we're gonna read what I find a fun book. It's one of my favorites. And stay safe, stay healthy, try to get some exercise. I'm going to say it's not all about video games and movies. It's also a little bit about moving around and making sure that, you're getting that exercise. Remember, we just did a whole series about why that exercise and good nutrition is important. All right, second grade, stay healthy, stay safe, stay happy.